auto-ionization constant of water.
The one America is not defending
So,
at all.
the auto-ionization constant of water is 10 to the negative 14. And basically, it is an equilibrium expression, just like every K value. Every K value is an equilibrium expression. And specifically, it's equal to 10 to the negative 14. And it's equal to the hydronium ion concentration to the, equal to the, or multiplied by the hydroxide ion concentration. And the equilibrium looks basically like this. Two H2O liquids goes to H3O plus and OH minus. Does that make sense so far? So, quick review of equilibrium expressions. A K value, which is an equilibrium expression, is equal to the concentration of the products over the concentration of the reactants. So we talked about that in April or 2 Aprils ago, depending on who you are. So again, the brackets are concentration. So any KW, or any K value, an equilibrium expression, is the concentration of the products over the concentration of the reactants. So far so good? Now for water, water molecules are in equilibrium with their ions. So 2 water molecules will be in equilibrium with a hydronium and a hydroxide. And the K value for that would be 10 to the negative 14, where we have H3O plus and OH minus over a liquid, but we don't show liquids in an aqueous equilibrium. Okay, remember this? So in an aqueous equilibria, you only show aqueous species. In a gaseous equilibria, you only show gaseous species. For now. When you get to college, things can change a little bit, but at this level of chemistry, aqueous is all aqueous, gaseous is all gaseous. Cool? Give me a thumbs up if that makes sense to you. Okay, I want to get some little feedback from you guys. All right, so water has an auto-ionization constant equilibrium of 10 to the negative 14. Now, if you take the P of all this, then you realize that, let me use a different color. If you take the P of all these things, then you get PKW, and you get pH, and POH, and 14. So if you take the P of all these things, then you get PKW equals 14 equals pH plus POH. Again, talked about it before, just to review because it's very, very important. How are we doing so far? Okay, so I took the negative logarithm of this, PKW, negative logarithm of this, 14. Negative logarithm of this product. Remember, the product of a logarithm is the sum of those logarithms. So A times B logarithm becomes logarithm A plus logarithm B. Okay. And fun fact, this is what I didn't come up with before. Fun fact, the product of a logarithm is subtraction. So if you took the logarithm of B over A, then it's going to be logarithm of B minus the logarithm of A. It's kind of fun. Cool? And that's what we do here. That's where we use this equation to get the Henderson-Hasselbalch. All right, so in an acidic solution, HA is going to be in equilibrium with its acidic anion plus H+. Now, HA is going to be aqueous, and the ions, of course, are obviously also going to be aqueous. So HA is an aqueous acid, an acid dissolved in water. So HA, for a weak acid, is going to be in equilibrium with A minus and H+. For a weak acid. Remember weak acids? Okay. For a strong acid, it's just all the way across. Okay. And then for a base, B will be in equilibrium with BH plus OH minus. Cool. And we talked. Okay, good.
That's for weak bases.
Weak bases, yes, weak bases. And we talked about the conjugates of weaks. A weak acid, remember conjugate? The idea of an acid can give up a proton and become a conjugate base, or a base can accept a proton and become a conjugate acid. And we talked about a strong acid has a negligible conjugate base. In other words, it's a base with negligible basic strength. Okay? So if you have a strong acid, it makes a conjugate base that doesn't really behave like a base at all. If you have a strong base, it makes a conjugate acid that doesn't really behave like an acid at all. Do you want some of my apple juice? Okay.
Sorry.
You're like, I froze this apple juice, and then I thought it out today, and it was like, oh, apple slush. So does that make sense? Now, a weak acid makes a conjugate base that is weak, and a weak base makes a conjugate acid that is weak. And a stronger, this is where things get dicey, a stronger weak acid makes a weaker conjugate weak base. And a weaker weak acid makes a stronger conjugate weak base. Okay? Basically, the conjugate is exactly the opposite. Strong acid, conjugate base. Weak acid that is weak makes a stronger weak conjugate base. Make sense? Okay. Any conjugates are basically, they have to be weak acid and weak bases. So these two relationships exist, that HA is in equilibrium with A minus and H plus. B is in equilibrium with B plus and OH minus. So you take the P's of these things, and you get something kind of interesting. So KA is the equilibrium constant for acid, A minus plus H plus over HA. KB is the BH plus, this is actually written right up there, OH minus, it's that poster I put up last week, over B. Okay, so that. Okay, and then, this is kind of cool, the KA, again, it's right up there, the KA multiplied by the KB will give you KW. Because of this conjugate relationship. If this value is very, very big, then this value has to be very, very small. Because KW is a constant, 10 to the negative 14. So if your Ka is a stronger weak acid, the conjugate base it makes will be weaker. And if your weak base is stronger, has a very big Kw, then your Ka, as long as they're all weak, will be smaller. Make sense? Conjugate acid, or acid, conjugate base. Base, conjugate acid. Cool? The product of the two, the acid multiplied its conjugate, will be 10 to the negative 14. How are we doing so far? It's dicey stuff, but we're gonna get there. Yeah.
So I understand the whole concept, but what is like a conjugate base again? Or like, how do you get it?
A conjugate base is an acid that has lost its proton. So HA is the acid, it's got its proton. A minus is the conjugate base. It is the species that has lost its proton. And the reason it acts like a base is because it can gain its proton and form the acid again, because this is an equilibrium. And if you had a strong acid, HA goes to A minus plus H plus, then it's only traveling in one direction. And a strong acid travels in one direction where its conjugate base cannot become an acid again. It has negligible acidity, negligible basicity strength. Cool? And you realize it's very strange. This is probably why they moved all acid base to AP away from chemistry 1. Whether I agree with that or not, doesn't matter. This is what they did. Okay, so a buffer. A buffer is a mixture of an acid with its conjugate base. And Henderson-Hasselbalch equation basically is this rubbed together with this gives you the Henderson-Hasselbalch equation. Anyway, so it's pretty cool. And basically what it says is if you have a mixture of an acid with its conjugate base, you can determine, using this equation, what the pKa would be with the pH. Or, if you have the pH, and you know what the compounds are, you could determine the pKa. And that's the question it's asking in the last lab. How can you use this information to determine the identity of your acid? I'll show you why, or how. First and foremost, okay, question.
What's the pKa?
The pKa is the negative logarithm of this equation.
Okay.
So negative logarithm of that, negative logarithm of that. So if you took the negative logarithm of this, this would be pKa equals Pa plus pH minus pHa. But we don't care about that. What we care about is it's the negative logarithm of a Ka value, which is identifiable to each acid, where each acid has a unique Ka value. Okay, so citric acid might be, I'm just pointing out here, might be 10 to the negative 3. Ascorbic acid might be 10 to the negative 5. Boric acid might be 10 to the negative 2. They all have an identifiable Ka. Yeah.
So if you were to be working with, like, basically what I'm asking is, why aren't bases in the equation? Why is it just the acids?
Don't know, but you could easily just replace this with OH, Kb, BH plus, and B.
Okay, so you just basically like subtract it from your
Yeah, yeah, because it would work either way. So if you were, the Henderson-Hasselbalch is written 4 acids, and it's on your formula chart 4
It's
acids.
because pH is what we measure by, and pH is acid.
Yeah.
And, okay.
Yeah,
I mean,
but yes, you could absolutely just say, oh, okay, rather than going to the pH, or rather than everything going back to acid, you could replace pH with POH, pKa with pKb, and then A minus. Instead of using the conjugate of an acid, you can conjugate the base. Conjugate base is BH plus, base plus proton. And then instead of HA, you just have B. And that would work. Okay, so it wants to know, how can you use the information to identify what acids you have present? And this is how. You have your pH curve. Let's look at the major points of our pH curve. We were adding, this is pH, and this is volume added. We were adding base, yeah? So where should our pH have started? High or low? Low. It's going to start low, and we're going whoosh. Okay? So ideally, this is what it would look like. Because we used very dilute weak acids and a strong base, this all got kind of squished, but this is basically how it works. Now, we didn't calibrate the pH sensor specifically because I don't know why we didn't do it. We just didn't do it. So the actual pH was a little dicey. We talked about this. So if you have a strong base and a weak acid, the equivalence point ends up with a slightly basic pH. Okay? If you have a strong acid and a strong base, the pH at equilibrium or equivalence is 7. And if you have a strong acid and a weak base, the equivalence point is slightly acidic. So the equivalence point should have been, for our weak base, or weak acids and strong bases, should have been in the neighborhood of 9-ish. It wasn't because we didn't calibrate, but that's the important thing here. Okay, so here's our equivalence point. Right in the middle, right there. By the way, if you took the first derivative of this, it goes, the derivative looks like this. In other words, slope. If you did the slope of it, it looks like this. And technically that's what we should do and say, oh, there it is, that's that high point. So this would be dpH, the volume. But anyway, all right, so back to this. At this point, you have a whole bunch, okay, with nothing added, no NaOH added. You have this relationship right here. Okay, you haven't added any base at all. you have mostly what? What species is mostly present? Of these three, it's the bracket. Of these three, which is mostly present before you add an E base? HA. Yeah, exactly. So there's mostly HA present. Remember, in a weak base, in a weak acid, there's more molecules than there are ions. Okay? Now, every time you add an OH, what happens to this relationship?
It's closer to 1, right?
Well, okay, from very, very small to less small.
Yes.
So every time you add an OH, something happens to this species. What does the OH react with?
The
The H plus. And remember, we're talking about this relationship here. If you add if you basically take an OH, the OH is going to attack the H plus. Hey, look at H plus, let's make water. Okay. Now, the equilibrium relationship we learned about was for everything you do to the EQ, I will undo the EQ. By reducing the H plus, where does this equilibrium shift? That way. Okay. In other words, every time you take that H plus away, an A minus gets produced from the HA. Does that make sense? To reestablish that equilibrium. By removing the H plus, that's, remember, up and over, down and 2. By removing the H plus, the equilibrium is going to shift that direction to replace the H plus. And to do that, that means the HA goes down and the A minus goes up. Does that idea make sense? Okay, that's just Le Chatelier's. So, over here, we got a whole bunch of HA, whole bunch of HA. Ha. There's a whole bunch of ha. And not much of anything else. Okay? And here, we have something really interesting that's happened. Right at that point, we have an equivalence point of the moles of H plus is equal to the moles of OH minus that we've added. Here's the really cool thing. If you have a lot of HA here, and basically none here, no HA anymore, if you have a whole bunch, you have almost all HA, and again, mathematically, when I say almost all, I mean like 10 to the negative 5 divided by, okay, almost all. There's a few H pluses, there's a few A minuses, but it's mostly HA. And when I say no HA, I really mean there's a few HA, but mostly not much. Okay? This is the nature of weak acids. You can't say all and none, you just say mostly none and mostly all. Mostly all HA, mostly no HA at the equivalence point. Okay, so far so good? So if there's mostly all HA here and mostly no HA here, what do you have between those 2 points? I'll write it down in a different way. So here we have, at this point, we have lots of HA, no A minus. And by no A minus, I mean very, very little. And up here, we have lots of A minus and no HA. And by no HA, I mean just a few. And right in between, you have approximately the concentration of A minus is approximately equal to the concentration of HA. At half the equivalence point, you have a situation where you have about the same amount of A minus and HA. Does this idea make sense? So here, whole bunch of HA, not much A minus. Here at the equivalence point, mostly A minus, not much HA. Do you understand why there's not much HA? We keep adding base and we keep adding base and we keep removing an HA and turning it into an A minus. Every time we add an OH, an HA becomes an A minus. So here, whole bunch of HA, a whole bunch of A minus, not much HA. Here, whole bunch of HA, not much A minus. Right in between, the two are about equal in concentration. Now, why is that important?
Wait,
Yes?
where's the right in between?
If this is, okay, so if this is 0 milliliters added, and this is 20 milliliters added, this is 10 milliliters added.
Okay.
Okay, so right in between is basically half the volume it took to get to the equivalence point. Thank you. Chris?
Can you find the H plus? The concentration of the H plus?
Yeah, you can, but something more profound than that.
Does that make that the log equal to just the log of 1?
And what's the log of 1? 0, exactly. So remember, 10 raised to the 0 power is 1. Anything raised to the 0 power is 1. So when these two things are equal, when this is 0.1 and this is 0.1, this is a logarithm of 1. And a logarithm of 1 is 0. So at that point, where you're at half of the equivalence point, the pH equals the pKa. When you find your equivalence point, at half that point, these two things will cancel out and your pH equals the pKa. I'm getting chills. Oh, it's so powerful. It's really, really handy. And something we're going to talk about in the equation. See how my box is going. Warping like a mofo. Okay, so let's summarize. We've learned that strong acids don't produce any conjugate base at all, or the base they produce isn't very basic at all. Strong bases produce a conjugate acid that's not really acidic at all. Weak acids are in equilibrium with their acidic anion and H+. Bases are in equilibrium with their conjugate acid and OH-. When you are doing a titration equation